All right, so we're going to do some examples. Again, I already said this, but whatever. I promise you, you'll see this on homework. I promise you, you'll see this on exam, probably on a final exam too. Because if you can understand these thin film problems, you really understand diffraction. I mean, interferences, okay? Now, something else I need to warn you about. So what we're going to do, we're going to figure out equations for constructive and destructive interference for different values of n. We're going to do all different cases, and we're going to figure them out. It's going to be, and here's the thing. You are not going to see these equations on the equation sheet. And furthermore, you should not memorize them. You should be able to figure them out. So that means you're going to have to think about this, what we're doing, all right? But you have to understand it. That's why I like these problems. You really have to understand it. I mean, hopefully nobody's going to memorize these things. You have to understand them. So let's go. All right, first of all, this is a totally exaggerated but useful diagram. What are you talking about? So, you know, when you read the problems, they always say that the light is perpendicular to this thin film or whatever, right? So the light is really perpendicular. But if you draw it that way, it'd just really be hard to interpret, you know? So it's much easier just to say, forget about that. Have the light come in at some angle, all right? And we're just going to exaggerate the angles like crazy, all right? So this is not physical. I don't care. It's useful, okay? That's the important thing. It's useful. And you know, you may have heard the saying, a picture's worth 1,000 words. Well, it's true here. If you understand this picture, you can do it. All right. First of all, so again, remember, this line is supposed to be perpendicular to this. This line is supposed to be perpendicular, right? We're just doing that to make it easy for us. So just pretend this line is straight, perpendicular, you know, perpendicular to this and this. All right. So the thickness of this film, like my anti-reflective coating or whatever, you know, it's T for thickness, okay? So what is the path difference between ray 1 and ray 2? Well, that should be obvious, I hope. The path length difference is just T plus T, 2T, you know? Okay? So the path length difference is 2T. So path length difference is 2T. And again, it's hard to swallow when you see that picture, but that's all right. All right. Here we go. All right, so what we're going to do, we're going to take each of these three situations. But what we want to do now is we want 1 and 2 to constructively interfere. After we do these three, we'll do the destructive case. But right now we want constructive interference. Okay? All right. So let's say that there are no lambda over 2 reflections, or no lambda over 2 flips, or no lambda over 2 shifts. Okay? In other words, this is less than, the n here is less than n here, and n here is less than n here. So this ray is not going to be inverted. This reflection is not going to be inverted. So there's no flips, okay? That's what I call it, a flip, all right? So this is what I'm talking about. I'm talking about, so I would say this is a flip, all right? A lambda over 2 flip. There's no flip here, okay? I'm just talking about this, right? Flip, no flip. Okay? All right. So let's say there are no flips. So therefore, we want this to constructively interfere with that. Now look at, there's no flips. So, I mean, so this one is the same as this one, right? They didn't get, you know, there's no shifting or anything like that. But wait a second. What's the only difference between 1 and 2? The path length difference, right? Ray 2 went down and up, whereas ray 1 just didn't go in here at all. So there's a path difference between this one and this one of 2T, okay? All right, so there's no flips, right? And so no flips. There's a path difference of 2T. All right, now we want constructive interference. If we want constructive interference, the path difference, 2t, what did we learn a while ago? The path difference equals a lambda, 2 lambda, 3 lambda, blah, 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 right? So we say 2t equals m lambda. That's all, okay? Now hold it, you gotta be careful. Where is the path difference happening? It's in the film, right? It's not up here, it's not down here, it's here. So when we say, you know, m lambda, you gotta be careful. It's m lambda film, and you'll see why in a minute. You gotta be super careful, all right? So there you go. If we want constructive interference, we don't have any flips. The path difference is m times lambda film. That's all. You're guaranteed to get constructive interference. All right, so hopefully that makes sense. Again, don't memorize. You have to understand this stuff. All right, let's do one flip. And see, it's just one flip. I don't care if it's this one or this one. It doesn't matter, right? All we're saying is that one of them is going to invert. Okay? Now look, if one of them inverts, that means, okay, let's say you have a wave like this. Then one of them inverts, so you have like this, right? Now, that's going to be destructive. We want constructive, right? We want constructive. So that means we're going to shift this thing. Well, how much are we going to shift it? A half a wavelength, right? Or 3 halves or 5 halves. Well, wait a second. What do we have to, what can we play with? We can play with the thickness of the film, right? Right? So if we shift this a half a wavelength, that means we want 2t equals half a wavelength. Yeah? We're taking this thing and shifting it half a wavelength. So it's going to be like this, because we want constructive interference. Well, not just a half, how about 3 halves? Or 5 halves, or whatever, you know? So that would be fine. So it's a nice, quick way of writing that. Okay, m minus a half lambda film. Because put 1 minus half is a half, so you get lambda over, you get a half times lambda film. If m is 2, you get 2 minus a half, which is 3 halves, so you get 3 halves. Now wait a second, how come I have a minus on here, not a plus? Well, actually you could put a plus if you want to. But if you put a plus, you don't want to start with 1. You'd have to start with 0, right? So we're just being lazy. We just want to use the same m for every situation here. So that's why we put a minus, okay? If you want to put a plus, you'd say here m is 1, 2, 3. Here you say m equals 0, 1, 2, 3. And here you say m equals 1, 2, 3. Whatever, doesn't really matter, right? I'm just saying this is lambda, 2 lambda, 3 lambda, not 0 lambda, because that doesn't make any sense, right? That would make this thing not exist. But here it's 1 half, 3 halves, 5 halves. Okay? All right, next one. Now we have 2 flips. So that means that this one inverts and this one inverts. Well, if they both invert, what's the net result? The same, right? I mean, they cancel each other out if you want to think of it that way. They both inverted, so they're basically in the same situation, right? But we want them to constructively interfere, so what does the path difference have to be? Same as that, right? Because, again, this is the same as that. So the path length difference has to just be m lambda again. Ta-da! Okay. All right. So that's great. Now, let's do this one. Okay. So the question typically asks for the thickness of the film. You know, like if you're gonna, you know, like if you're working at some kind of a place where they're putting a thin film on something, and it's really expensive. You know, you want to put as little as you can, right? So you want to solve for t. So for that one, let's say that 2t equals m lambda film. Okay. Well, you know, typically you don't know what the wavelength of the light in the film is. You know what the wavelength of light in a vacuum is, you know, or air or something like that. So this is true but sort of useless, all right? But now you got to remember, lambda medium equals lambda vacuum all over n medium. Remember we saw that a little while ago? So you got to use this. So then you're going to just substitute, right? So it's going to be m lambda vacuum over n film. All right? So I just substituted for lambda film. Lambda film equals lambda vacuum over n film. Because you know, when you do a problem like that, they'll always tell you the wavelength of light in the vacuum or the air. They're not exactly the same, by the way, but they're close enough. So that's what, so, all right, so that's 2T. So therefore, the thickness of the film is just m lambda vac over 2n film. And you can see, right, this is m, right? You know, that's 1, 2, 3, 4, 5, whatever. It's an integer, you know? So it's best really to write it like this. Okay, so you know, if you want the absolute thinnest film, you're going to put m equals 1. But maybe that's not a good idea. Like if it were anti-reflective coating on your glasses, you know, maybe making the thinnest would not be good because, you know, when you clean your glasses, maybe it would wipe it off or something like that. I don't know, whatever. But anyway, I'm just saying there's different values where you get constructive interference. All right, now let's do destructive interference. Destructive interference. All right, let's say there's 0 flips. So therefore, what's the only difference? The only difference is the path difference, right? This guy is going 2t more than that guy. All right? We want destructive interference. All we have, we don't have any flips, we don't have any inversions. All we have is the path difference. Well, come on, we learned this before, right? So 2t is the path difference. If we want destructive interference, we want this to be a half wavelength, 3 halves, 5 halves, whatever, right? Agree? So we want 2t equals, let's see, we want to start m equals 1 just like last time. Okay? So we're going to say m minus a half lambda film. Make sense? Where m equals 1, 2, 3, on and on. So that's going to guarantee we have destructive interference. All right, now let's do the next one. Now let's say we have one reflection. Again, I don't care if it's here or here, but we have one reflection. So now, you know, now we have one wave like this, but the other one is flipped a half a wavelength, so it's already like that. Okay, so look, if we just leave that alone, we're going to get destructive interference, right? So what do we want the path difference to be? Well, we don't want the path difference to mess it up. We already have destructive interference, right? So if the path difference is a 1 wavelength or 2 or 3, it's going to stay like this, and we're going to get destructive interference. So there you go. So we're just going to say that the path difference is just m lambda, right? Okay, and now you already know how to do the next one. So if this flips and this flips, what's the net result? Nothing, right? Nothing. And so this is always going to be the same as that. Ta-da! All right, so you should be able to figure out these 3 as well as these 3, okay? Because they will not be given to you. All right, so and you need to understand them. And if I went too fast, just read the book and think about it. You got to think about it. Maybe rewatch the video or something, but think about it until you understand it. Okay, I want to do a real example. So just like what you're going to see in your problem set in your exams. A layer of transparent plastic on glass looks dark when viewed in reflected light whose wavelength is 589 nanometers in a vacuum. Find the 2 smallest possible non-zero values for the thickness of the layer. Okay. The most important thing is to draw the picture correctly. So let's do it. Okay, so we have plastic on glass. So this is plastic, and this is glass. Now, what's above it? Well, air, right? I mean, right? So this is air. Okay. So that's the first thing. Now you're going to write down what you know. So air, N equals 1. Plastic, N equals 1.61. And glass, N equals 1.52. All right. Now, there's one ray of light coming in. So this one guy goes there, and it reflects. I'll call that number 1. And again, we're going to make crazy angles. Even so, oh, it doesn't say it. Usually it will say that the light is coming in perpendicular to the film. But we don't care. We're going to draw it to make it nice so we can figure out what's going on. And then remember, some of it goes through, and it reflects here. And we're going to learn that this is not parallel to this, but I don't care now. That's later on. So that's 2. Okay? So here's my great picture. All right? Hey, even different colors. Woohoo, right? What do you know? All right, so where are the reflections? Reflections are here and here. Okay? So let's look at number 1. Number 1. It's going from air to plastic, 1 to 1.61. What's going to happen? It's going to flip. So again, I just call it a lambda over 2 flip, meaning like an inversion, you know? Okay, how about 2? 2 goes from plastic to glass, 1.61 to 1.52, no flip. So number 2, no flip. Okay, so this one is inverted. This one is not inverted. So if we didn't have, oh, I forgot to do this. Don't forget to label the thickness of the film. All right, oops. Okay. All right, so this one's flipped, this one's not flipped. So that if we didn't have any path difference, how would this one interfere with that one? One is inverted, one is not inverted. Destructively interference, right? So without the path difference, we would get destructive interference. Now, what are we supposed to get? Constructive or destructive? You got to read it. Okay, so they always give you hints. So what does it say? A layer of plastic looks dark. It looks dark. So what kind of interference is that? That's destructive interference, right? So what we want, and you got to figure that out from the words if they want constructive or destructive. We want destructive. We want destructive interference. Okay, you got to figure that out. Awesome. All right, so let's see. We have one flip, so we're going to get destructive interference if we don't have a path difference. But we have a path difference, 2t. Well, we want to maintain that destructive interference. So what do we want the path difference to be? Wavelength, 2 wavelengths, 3 wavelengths, right? So what we want the path difference to be m lambda film, which is plastic. Okay, now again, you know, you got to figure that out. All right, you got to figure it out. You can't. There's no equations here. I mean, I'm not going to give you any equations. All right. Oh, I shouldn't have done that. That was stupid. Okay, hold on. All right. So that means that T, over here. So T equals m lambda plastic divided by 2, right? But what's lambda plastic? So it's lambda plastic is lambda vac. Then we have the 2, n plastic, right? Because remember, lambda medium equals lambda vac over n medium. We use it a lot, you know? All right, so there's the equation, okay? So we have thickness equals m lambda vac over 2n plastic. All right, so now let's just plug in the numbers, you know? So, okay, so m equals 1. So the thickness is lambda vac over 2n plastic. Okay, what's lambda vac? 589 nanometers over 2. What's n plastic? 1.61, right? And that comes out to be 183 nanometers. And then for m equals 2, it's just twice that, right? It's just twice that, right? Just twice that. So it's just, so the thickness is 2 times 183 nanometers, which is 366 nanometers. So there you go. That's how to do it. So they might do stuff like this, right? Find the 2 smallest, you know, or 3 smallest. I mean, whatever, you know. You never know. Okay, let's do okay, if this were in class, you would solve this in groups. So if you would please do this on your own. Seriously, do it on your own. I mean, I'm going to do it in a minute, right? But do it on your own. You have to be able to figure this out, right? So do it on your own and then come back to the video. Okay, let's do it. So, as always, draw the picture. Okay, so let's see, we have benzene. So N equals 1.501. Benzene. And let's see, what is the minimum thickness of benzene? That will, oh, and then it says a glass slide supports the film. So N equals 1.62. This is the glass. And again, it's always air, right? And so N equals 1 for air. Okay, so here's the thickness. Okay, ray number 1 comes in and reflects. And this one goes here, reflects here. There you go. All right? So that's, I mean, this is like the pictorial representation that we learned when we did kinematics. Remember that in the olden days? Physics 105. So you got to get this. If you can get this, you're pretty much almost done, you know? Okay. But yeah, see here. Look at what it says. It says, what's the minimum thickness of the film that results, now here they're nice, come on. It results in constructive interference. Usually they say like it will be bright or something like that. So we know it's constructive, and look at what it says. When viewed at normal incidence, normal means perpendicular. So see what I mean? These rays of light are really perpendicular to the films, but whatever. You don't draw it that way. Okay? We don't care, right? All right, so let's do it. So you draw the picture. That's crucial. Then you just go through the analysis. Number 1 goes from air to benzene, right? Air to benzene, small to large. It flips. So number 1 flips, lambda over 2 flip, or whatever you want to call it, inversion, reflection, whatever you, I don't care. Call it whatever you want to do, right? Okay, number 2. Let's see, it goes from benzene to glass. Oh, so it goes from, right here. So it goes from 1.5 to 1.6. So small to large. What happens? Flips. Okay? So this also flips. Lambda over 2 flip. So that means that both of the waves are inverted. Now they're both inverted, so that means they're the same, right? They're the same. So what's the only difference between 1 and 2? The path length difference, you know? Okay, now it says, they're incredibly nice, it says constructive interference. Okay, well the waves, they both flip, so they're the same, but the only difference is the path length. If we want it to remain constructive interference, we just want the thickness to be m lambda, right? Right? That's it. Awesome. So, but we want the t, so the t is m lambda film over 2. Now again, they never will give you the wavelength, I shouldn't say never, but I can't imagine, I don't remember ever seeing it, when they give you the wavelength of light in a film. They always give you the wavelength of light in a vacuum. If they don't even say it, you just assume it's vacuum. So you got to say that this equals m lambda vacuum over 2 sorry, 2N film. Okay, so let's do it. So the thickness, so what does it say? The minimum, right? Cheapskates. So we want m equals 1. So the thickness is just 1 times lambda vac, 615 nanometers over 2. Okay, N film, this is the film, right? The benzene. So it's 2 times 1.501. And notice this doesn't have, these don't have units, right? N doesn't have units because it's a speed over a speed. So what does that come out to be? Comes out to be 204.86 nanometers. All right, you better know how to do that because I promise you you'll see it again. All right, let's quit.